Hello and welcome to this video on the conservation of momentum, which is part of the forces of motion module for OCR A-Level Physics in the subtopic of Newton's laws of momentum. So if we've been successful and we've learned in today's lesson, we should be able to define and describe the conservation of momentum, calculate values based on the conservation of momentum in one dimension, and calculate the values based on the conservation of momentum in two dimensions. So in this lesson, we're going to look at the following parts of the OCR A-Level Physics specification: 3.5.2 collisions. Now, the linear momentum of an object is dependent on two factors of the object: the mass of the object and the velocity of the object. Now, we can express this in the form of an equation that momentum is equal to mass times by velocity. Now, we know that momentum is similar to kinetic energy as it contains the same terms. Momentum is mass times by velocity, and kinetic energy is a half mv squared. Now, we can symbolize this equation with the symbols P equals mv. Now, linear momentum is given the symbol P as is the first letter of the Latin translation of momentum. Now, in collisions and explosions, the total momentum is conserved if the system is closed. So this means that the total momentum of a system before is the same as the total momentum of a system afterwards. So we can say the total momentum before the collision equals the total momentum afterwards. Now, this is derived from Newton's laws of motion. So we can say that the total momentum before, which is momentum 1 plus momentum 2, will equal the total momentum after, momentum 1 plus momentum 2. Now, the individual objects in the system can change their momentum in an event, but the overall momentum of the system must stay constant. So, for example, if beforehand object 1 had a momentum of 2 kg meters per second and object 2 had a momentum of 0 kg meters per second, well then afterwards object 1 could have a momentum of 1 kg meter per second, as can object 2. So whilst the individual objects have changed momentum, the total overall momentum has stayed the same. Now, for an individual object to change momentum and have an impulse acting on it, a resultant force must be placed on the object. Now, we can say that the total momentum before, which is mass 1 times by velocity 1 plus mass 2 times by velocity 2, must equal the total momentum afterwards, where mass 1 times by velocity 1 plus mass 2 times by velocity 2. Now, the definition of the law of conservation of momentum states that it only applies when no external forces act. Now, an external force is a force that acts on an object in a system or the system itself from outside the system. So common examples of external forces include friction or weight. Now, systems with no external forces may be described as closed or isolated. So, as we said, for a system of objects, the total momentum of the system before equals the total momentum of the system afterwards, as long as there's no external forces on the system. Now, this can be observed in a collision where objects hit each other and move away with each other. Or we can consider any system which has at least one dynamic object before contact a collision. Now, it's important to note that the momentums of individual objects in the systems can change, but the total momentum of the system must remain constant. Now, as the total momentum remains constant, when the mass of a moving object increases after a collision, the velocity will decrease. So it also indicates to us that if the mass of the object increases as the two objects couple together, their velocity will decrease. Or if an object splits, when the mass decreases, the velocity will increase. So let's consider the following collision. What's the velocity of the two balls stuck together after the collision? So the first step is to work out the momentum for the side of the collision you can do. So beforehand, it's 2 times by 5 plus 4 times by 0. So 10 plus 0 is 10 kg meters per second. You then remember that the total momentum before equals the total momentum afterwards. So the total momentum is 10 kg meters per second. Then finally, we can say that momentum is equal to mass times by velocity. So velocity is equal to momentum over mass. So it's 10 over 6, which is 1.7 meters per second. Now, in an explosion, the total momentum of a system is 0. So in an explosion, where the motion where an object starts at rest and moves away from each other conserves momentum. Beforehand, the object is not moving. This means it has a total momentum of 0. So for a momentum to be conserved, the total momentum of the system must be 0. Now, after an explosion, both objects have a non-zero momentum. Now, the two objects are produced as fragments of the initial object. Now, as we said, the total overall momentum must be zero because this conserves momentum. Now, this occurs as the individual momentums are in opposite signs. This means that one momentum is positive and the other momentum is negative. This occurs as the two fragments are moving in an opposite direction, and this opposite direction gives them opposite signs. So as we said, the overall total momentum of a system after the explosion must be zero to conserve momentum. So one will be positive, for example, plus 20 kilogram meters per second, and one will be negative, such as minus 20 kilogram meters per second, to get your overall answer to be 0 kilogram meters per second. Now, this is shown when you consider a gun and a bullet. The recoil in any explosion can be explained by the conservation of momentum. So the total momentum is equal to 0 because the total momentum before equals 0. So before it explodes, the gun and the bullet are not moving. So therefore, the system has no momentum. So this means the system has no total momentum, which must be conserved in any event such as an explosion. So when the object is fired, the gun has a momentum and so does the bullet. But they must cancel out to give a total value of 0 because the total momentum afterwards is 0. So this means that the gun goes in the opposite direction to the bullet. The gun has a recoil. Now, the gun has a much larger mass than the bullet. So since momentum is mass times by velocity, the gun must have a lower velocity than the bullet to have the same magnitude of momentum, because we need the same magnitude of momentum from either side. So we can say that the momentum of the bullet equals the momentum of the gun. So we can say the mass of the bullet times by the velocity of the bullet is equal to the mass of the gun times by the velocity of the gun, which we can rearrange to say that 0 is equal to the mass of the gun times by the velocity of the gun minus the mass of the bullet times by the velocity of the bullet. Or 0 is equal to mgvg minus mbvb. So let's have a look at the following example. What's the velocity of bomb fragment 1? So the first step is to work out the momentum for the fragment of the explosion you can do. So the momentum of fragment 2 is 2 times by 7, which is 14 kilogram meters per second. As the momentum before equals the momentum afterwards, if beforehand was 0, afterwards must equal 0. So this tells us if fragment 2 has a momentum of plus 14 kilogram meters per second, well then the momentum of fragment 1 must be minus 14 kilogram meters per second. We can then say that momentum is mass times by velocity, so velocity is momentum over mass, so it's minus 14 over 3 minus 4.7 meters per second. The negative value indicates that it's moving in the opposite direction to the other fragment. Now, momentum can be conserved in both one-dimensional and two-dimensional problems. A one-dimensional problem occurs when collisions take place in one plane, either the vertical or the horizontal. A two-dimensional problem occurs when collisions take place in both planes, both the horizontal and the vertical. Now, since momentum is a vector, in 2D it can be split up into its x and y components. So in collisions and interactions, the linear momentum is conserved in all directions. So using the conservation of linear momentum as well as resolving vectors, it's possible to calculate changes in momentum. So below shows an object A moving to the right with momentum. It collides with stationary object B. After the collision, A and B move off in different directions with momenta P1 and P2 respectively as shown. Since linear momentum must be conserved, the vector sum of P1 and P2, the total final momentum, must equal P, the initial momentum. So what you can therefore do is you can draw a vector triangle to add the two vectors together, P1 and P2, and then work out your value from this. Another example would be below shows a general collision involving two masses, M1 and M2. The white object travels at a velocity v0 and collides with the stationary black object. After the collision, the white object travels at theta 1 and it's with the original direction with velocity 1, and the black object travels at theta 2 with a velocity v2. Now, the momentum in any direction must be conserved. In this case, the momentum must remain the same in the x and the y direction. So we can say, horizontally, the total initial momentum is equal to the total final momentum. So it'll be m1v0 is equal to m1v1 cos theta 1 plus m2v2 cos theta 2, because we're now looking at the horizontal component of the velocity. And vertically, we know that the total initial momentum is equal to the total final momentum. So m1v0 equals m1v1 sine theta 1 plus m2v2 sine theta 2. Again, we're now looking at the vertical component of the velocity. So let's have a look at the following collision. A 160 gram white ball travelling at 4 meters per second hits a stationary 170 gram black ball. After the impact, the ball moves apart at approximately 90 degrees to each other. With the white ball travelling at 2.5 meters per second, calculate the final velocity of the black ball. So step 1 is to find the initial momentum of the white ball. So it's 160 times 10 to the minus 3 times by 4, which is 0.64 kilogram meters per second. The initial momentum of the black ball is 0 because it's stationary. Now the final momentum of the white ball after the impact is 160 times 10 to the minus 3 times by its new velocity, which is 2.5, which is 0.40 kilogram meters per second. We can then use this information to draw a vector diagram which sums those two values, the 0.40 kilogram meters per second and 0.64 kilogram meters per second. We can then use this triangle to have the Pythagorean theorem work out the final momentum, where we can say, as it's a right angle triangle, that p squared is going to equal 0.64 squared minus 0.40 squared. Now remember, 0.64 is going to be in the hypotenuse because it is the overall value afterwards. So therefore, it allows us to work out the initial component to start off with. Or to finish with, sorry. So therefore it's 0.64 squared minus 0.40 squared, which is 0.25. That square rooted is 0.50 kilogram meters per second. Now that's the momentum of the black ball. So therefore, what's the velocity? Well, we know that momentum is mass times by velocity. Velocity is momentum over velocity. So therefore it's going to be equal to 0.50 over 0.170, which is 2.9 meters per second. So in this lesson, we've looked at the principle of conservation of momentum. We've looked at collisions and interactions of bodies in 1 and 2 dimensions. So if we've been successful, and we've learnt in today's lesson, we can define and describe the conservation of momentum, calculate values based on the conservation of momentum in 1D, and calculate values based on the conservation of momentum in 2D. So thank you for watching this lesson on the conservation of momentum, which is part of the forces in motion module in the subtopic of Newton's laws and momentum, which is part of our OCR A-Level Physics specification. Thank you so much and have a lovely day.